Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. In the last lecture, we were discussing about the laminar and turbulent flow. So, we have seen how laminar and turbulent flow are created in nature, and we were discussing about its various kinds of behavior and how we can demonstrate or how we can classify between laminar and turbulent flow by Reynolds experiment. So, we have seen that with respect to the dimensionless number, Reynolds number, we can classify the the flow in either in open channel or in pipes as laminar or turbulent. So, that classification also we have seen. Then we were discussing in detail about the various kinds of laminar flow. So, we have seen in the one of the first demonstration the flow between two fixed parallel plates, and then we have seen the plane poisson flow. So, now in today's lecture we will be discussing further on the flow between parallel plates, but whenever a plate is moving. So, the first case which we have seen last time is whenever two plates are fixed like this, here you can see if these are two plates, then it is fixed, then what happens if a flow is between. So, that is the plane poisson flow that we have seen, and then we have derived the expression for velocity and shear stress and discharge, various flow parameters we have derived for plane poisson flow, that means the flow between two parallel plates. So, the plates are of infinite length, and then all the properties we have seen. So, in today's case we will be discussing the laminar flow between parallel plates, but one plate is moving. So, here two infinite, if you assume that there are two infinite plates like this, and then if the flow is between the plate and one plate is moving with a velocity velocity u. So, then how we can derive the various the flow parameters like velocity, discharge, and then the shear stress. So, here you can see in this slide the flow between two parallel plates, but one of the plate is at rest and another one moves in its plane with a velocity u. So, here the figure shows, here is the x axis if you draw, and y axis is here. The distance between the plates is t, and then u is the velocity of the upper plate. So, this is the case. Typical flow has got a number of applications, like whenever belt is moving in a fluid stream and then carrying some chemicals. So, these different applications are there with respect to this QT flow or the laminar flow between parallel plates. So, here the case is demonstrated. So, now we want to derive the velocity, shear stress, and the discharge. So, here now we have seen that earlier plane poisson flow, we have seen the case that the forces acting are the shear force and then the pressure force. So, now if you consider just a fluid element of thickness dx, and then we can, the various forces acting are the pressure force on both sides of the element and then the shear force. So, now the earlier case for the plane poisson flow, we have seen that the expression for this kinds of flow. When we write the, say for example, if you consider the case here, now say the one plate is here and now the second plate is moving with a velocity u. So, this is u and t is the distance. So, now we will be considering here to derive an expression for the velocity of flow between the plates. So, we will be just considering a fluid element of size dx by dy, and then say here the pressure force P and here the other side P plus dp by dx we will be considering, and then the shear force on both sides. So, correspondingly with respect to the plane Poisson flow, say we have seen the equation we have derived is dp by dx is mu d square say ux by dy square. So, corresponding say with respect to this with respect to the plane Poisson flow or with respect to the flow between two fixed parallel plates, only the difference is that the upper plate is moving. So, the equation is same, the basic equation is same, the basic equation is written here dp by dx is equal to mu into d square ux by dy square. So, this is the governing equation with respect to the Q-type flow, and then the boundary conditions are at y is equal to 0, that means on this plane at y is equal to 0 due to the no slip boundary condition, the velocity u is equal to 0, and at y is equal to t, then you can see that the velocity u is equal to u. So, that are the boundary conditions. So, the boundary conditions at y is equal to 0, ux equal to 0, and at y is equal to t, ux equal to u. So, now as we discussed in the case of plane Poisson flow between two fixed parallel plates, now to derive an expression for the velocity we can integrate this expression twice, so that we will get the expression for velocity. So, now if you integrate twice with respect to y gives ux is equal to 1 by 2 mu dp by dx y square plus c1 y plus c2, where c1 and c2 are constants of integration. Then we can use this both boundary condition as we have seen here, the boundary condition here u is equal to 0 at t is y is equal to 0, that is one boundary condition. Second boundary condition is u is equal to u at y is equal to t. So, here to find out these two unknown constants C1 and C2, we can use the boundary condition. So, if you use the boundary condition with respect to the second boundary condition, that means at with respect to the first boundary condition, say at y is equal to 0, if you apply, then we will get these terms goes, and so we get C2 is equal to 0, and if you apply the second boundary condition at y is equal to t, u is equal to u, then we get C1 is equal to u by t minus 1 by 2 mu dp by dx into t. So, now we got the constants C1 and C2, and then we can substitute back the constant C1 and C2 into this equation number 2. So, that we will get an expression for the velocity. So, finally, we get the velocity in the x direction ux is equal to y by t into capital U, which is the velocity of the plate, moving plate, plus y by 2 mu dp by dx into y minus t. So, this gives an expression for the velocity between the flow between two parallel plates. Upper plate is moving with a velocity capital U. So, this we can say, as I mentioned earlier, there are number of applications for this Q-type flow, so that we can say utilize this expression, this analytic derived expression to find out the velocity in various practical cases. And then from the velocity distribution, so now say other parameters such as shear distribution and discharge at any section can be found. So, as we have seen earlier in the case of plane Poisson flow, first we get an expression for the velocity, and then from that we can derive the discharge passing, or we can derive the other parameters like shear stress. So, now if say for example, this particular case, if dp by dx is equal to 0, then we say that say here in the earlier expression, if dp by dx is equal to 0 means this term, this second term goes, and then we get ux equal to y by t into u. So, this kind of flow we say that shear flow, wherever dp by dx, the pressure gradient in the x direction dp by dx is equal to 0, that kind of flow is called the shear flow. So, in that case we can get the velocity is equal to a simple expression y by t into u. So, this is called a shear flow. And then the velocity is concerned, say the velocity distribution for Q-type flow. So, if we plot, so here you can see that this plate is fixed, lower plate is fixed and upper plate is moving with a velocity capital U, and the flow is in this direction. So, if you plot the velocity distribution of the flow between these two plates, say for various a parameter called p, which we can define as this, say minus b square by 2 mu dp by dx. So, where b is the distance between these two plates. So, for various p we can plot the velocity like this. So, you can see that when p is equal to say 0, then it is linear, and then p is equal to 1, it is going like this, and p is equal to 2, it is this direction. So, like that for various these parameters we can plot the velocity distribution. So, here this b is equal to t, that means the distance between the upper and lower plate, and this figure is taken from the fluid mechanics book by Munson and others 2002. So, like this now we can plot the velocity, and then as I mentioned, say now once we velocity we can get the expression for the shear stress. So, shear stress is tau is equal to mu into du by dy. So, from which we can just take a derivative of the velocity, and then we can multiply it by say mu, so the dynamic coefficient of viscosity, so that we can get the shear stress. And then if we want to find out the flow between these two parallel plates, then we can integrate between 0 to t of this velocity going. So, the velocity into area, so that will give the discharge passing, so that we can integrate between these two and to get an expression for the discharge passing through the between these two plates. So, like that various parameters can be found out. So, this is called a Q-type flow, which has got a number of practical applications in various engineering problems. So, now before further discussing one of the application, we will discuss one of the numerical example with respect to this Q-type flow. So, here we consider the numerical example, we consider two horizontal parallel plates which are placed 5 centimeter apart. One of the plate is stationary, and other one moves parallel to the stationary plate at velocity of 50 centimeter per second. The pressure measured at one point in a fluid contained between plates is of 5 kilogram per centimeter square, and at another point 50 meter away in the direction of flow, the pressure is measured as 5.2 kilogram per centimeter. And then we have to find, so if the coefficient dynamic viscosity is given 5 as mu is equal to 5 Poisses, we have to get an expression for the velocity distribution in the flow, and then what is the rate of flow, and that means how much is the discharge passing and its direction, and then find shear stress at boundaries. How does shear stress vary? So, these are the case. So, now the problem is that here we have got a one fixed plate, and another plate is moving with respect to with a velocity 50 centimeter per second, and the distance between the plate is 5 centimeter. Then the fluid is passing between these plates, and its dynamic viscosity is 5 Poisses. So, we want to find out, we want to derive an expression for the velocity, and then rate of flow and shear stress. So, this is the problem. So, as we have seen in the previous derivation, we have derived an expression for the velocity. So, that expression we can directly utilize here. So, here the relation obtained for Q-type flow is directly used. So, the expression is ux is equal to y by t into u plus y by 2 mu dp by dx into y by t. So, that we have already derived earlier, and then for this particular problem the pressure gradient is given between 2 points, say within that between the plates 2 points the pressures are given. So, say with respect to this we can find out the dp by dx. So, we can take the difference between the pressure and the distance is also given. So, that we get dp by dx, the pressure gradient dp by dx is equal to P2 minus P1 by L. So, here 5.2 minus 5 by this distance is 50. So, 50 and then the unit is converted to meter. So, that we get dp by dx is equal to 40 kilogram per meter cube with respect to this dp by dx. Now, you can see that it implies that the pressure gradient is adverse. So, the pressure is positive, dp by dx is positive. So, pressure gradient is adverse. So, now the coefficient of viscosity mu is given as 5 poise. So, that we can write as that is equal to 1 by 98.1 kilogram second per meter square. So, we are converting all into the MKS system, and then finally we can substitute back to the equation. So, now all the parameters are known here. So, we can get an expression for the velocity. So, ux is equal to, say in the previous expression this t is or 5 centimeter. So, 0.05 and u is 0.5 meter and dp by dx is obtained as 40, and then t is also 5 centimeter and mu is 5 by 98.1. So, now we can substitute back. So, the velocity ux is equal to y by 0.05 into 0.5 plus y by 2 into mu is 5 by 98.1 into 40 into y minus 0.05. So, from this we get an expression for the velocity as ux is equal to 392.4 y square minus 9.62 y. So, we finally we got an expression for the velocity. So, by substituting the various values. So, now once we get an expression for velocity, as we discussed the discharge passing between the plate, the fluid flow between the plate, and then also the shear stress can be calculated. So, the discharge, the rate of flow per meter width is given. So, if we can integrate between 0 to t ux dy. So, if you integrate t is 5 centimeters. So, integrate 0 to 0.05 and the velocity 392.4 y square minus 9.62 y dy. So, this we can integrate between the limits of 0 to 0.05. So, that gives the discharge rate of flow per meter width. This is per meter width as 0.004325 cumex or meter cube per second. So, like this, once the velocity is known, we can find out the rate of flow per meter width, and then the shear stress at the boundary if you want to find out. So, then we can write tau 0 is equal to mu into dux by dy at y is equal to 0. So, that we can substitute back all various values 5 by 98.1 into 392.4 into 2y. So, du, so here already ux is known. So, this we can just take a derivative del ux by del y we can find out, and then we can put here as shown to find out the shear stress. So, shear stress tau 0 at y is equal to 0 mu into dux by dy. So, that is equal to 5 by 98.1 into 392.4 into 2y minus 9.62. So, at y is equal to 0, the boundary shear stress can be found, that is equal to minus 0.49 kilogram per meter square. So, this gives the shear stress, and then to get a relationship for the shear stress at any point in the fluid, we can just take tau is equal to mu into dux by dy. So, that gives the shear stress. So, the shear stress we can get an expression by taking the derivative of the velocity expression, that gives us mu into 784.8 into y minus 9.62. So, this gives the relation for the shear stress. So, like this we can find out the various parameters. So, now for this case, if you plot the various say the velocity, and then say now as we have seen here, we have the moving plate with the 50 centimeter per second, and here the fixed plate. So, now as we have seen earlier case. So, you can see that the various, say, the velocity variation. So, if we plot, say, here the bottom the velocity is 0. So, this you will get an expression something like this. So, here it is 0.5 meter per second and here it is 0. So, we can find out the velocity where it will be 0 by equating say this velocity expression to say 0. We will get where the position where the velocity become 0. So, similar way, if we plot this is the velocity distribution in this particular case, and then if you plot the shear stress, you can see that it will be something like say it will be varying at some point it will be 0, and then say here we have a value, and on the upper plate also we have a value. So, it will be varying like this. So, this is the variation of shear stress. So, from this expression we can find out the variation of the velocity and then the variation of the shear stress. So, like this various problems with respect to the Q-tape flow that we have seen, that means one plate is fixed and other plate is moving, we can solve. So, now say we will discuss one more case here. So, first we discuss, that means two plates say of infinite say length, it is two plates are fixed, and say then we have seen that one plate is moving, and then now we will derive an expression whenever both plates. So, that means two plates are placed like this of infinite length or breadth, and then first case is both are fixed, and then we have derived the expression for the velocity and shear stress and other parameters, and second case was first the upper plate was moving like this with the velocity, and then we found the expression for the fluid velocity and shear stress and then discharge. And in this third case we will be discussing wherever both plates, one plate is moving, upper plate is moving with the velocity u in the right hand direction, and then the lower plate is moving with the velocity v in the opposite direction, that means to the left hand direction. So, two plates are there, and then we want to find out an expression for the velocity and other parameters when both plates, the upper plate is moving to the right hand side and lower plate is moving to the left hand side with the velocity. So, now again here again the difference is again the boundary conditions. So, now the laminar flow between parallel plates moving in opposite direction. So, flow between two parallel plates, one of the plate is moving to the right, and as here it is demonstrated in the figure. So, this plate is moving with the upper plate is moving with the velocity u, and lower plate is moving to the left hand side with the velocity v. So, we want to find out expression for velocity, shear stress and other parameters. So, here the distance between the plate is b, and as in the previous case we will say we will consider a fluid element of size dx dy, and then we will find out the various forces on that fluid element, and then we will use the Newton's second law of motion to derive an expression. So, here now all the cases what we are considering is a steady state. So, time component is not coming, and then the acceleration is also not coming to picture. So, now only the Newton's second law, that means that the effective forces, total force on the fluid element we are equating with respect to the case. So, here also as in the previous case the forces are the pressure force on to the left hand side, or to the both p dy on this side and other side p plus dp by dx into dx into dy, and then we have the shear stress. So, here if it is tau dx on the bottom and top of the fluid element, it is tau plus d tau by dy into dx. So, the principle is essentially same. We are considering the problem in the very similar way. So, in that case now if we apply the Newton's second law, equation of motion for steady incompressible flow, then we can write the expression as p into dy minus p plus dp by dx into dy plus tau plus d tau by dy into dx minus tau dx equal to 0. So, the shear forces and then the normal forces, pressure forces get equator to 0, algebraic sum is equator to 0. So, now we can simplify this expression to get an expression for the velocity as we did in the previous two cases of the plane Poisson flow and then Qt flow. So, now if you simplify and then divide by dx into dy in 1 with respect to this expression, we will finally get dp by dx is equal to d tau by dy. So, the expression, so here as we can see that finally we are getting a simple expression when we are using the first principle Newton's second law motion, we are finally, since only the forces are considered, the case is steady incompressible. So, obviously the equations are becoming almost same way, only with slight differences, and then only changes with respect to the boundary conditions. So, here again we are getting dp by dx is equal to d tau by dy, and now for laminar flow, as we have seen, we can use Newton's law of viscosity, tau is equal to mu into du by dy, and then we can substitute for the shear stress expression tau mu into du by dy, and then finally we can get the expression. So, if we put it back to the earlier equation, here dp by dx is equal to d tau by dy, we get mu into d square u by dy square, that is equal to dp by dx. So, this is the final expression, and then as we did in the previous case, here also we can integrate twice, 2 times, and then we can apply the boundary conditions, and then we can find out the integration constants, and finally we can get an expression for the velocity. So, as shown in this slide, so if you integrate twice, we get u is equal to 1 by 2 mu dp by dx into y square plus ay plus b, where a and b are the constant of integration. So, here again we have got two boundary conditions, as I mentioned. Say here the plates are moving with the velocity. So, here on the upper plate we know the velocity u is equal to capital U on the top of the plate, and the bottom of the plate u is equal to v minus v in the other direction. So, the boundary conditions are known. So, we can just substitute here to find out the constant of integration a and b. We can write at y is equal to 0, u is equal to minus v, and then at y is equal to b, u is equal to u. So, now these are the boundary conditions. These boundary conditions we can substitute back, so that finally minus v is equal to 1 by 2 mu dp by dx into 0 for the first boundary condition plus a into 0 plus b. So, we get b is equal to minus v, and then if we substitute for at b, u is equal to u. So, we get u is equal to 1 by 2 mu dp by dx b square plus ab plus minus v, and finally we get the constant a is equal to u by b plus v by b minus 1 by 2 mu dp by dx into b, and finally we get now the constants a and b are found. So, we can substitute back to the earlier equation, and then finally we get the expression for the velocity for this particular case as u is equal to capital U plus v into y by b minus 1 by 2 mu dp by dx into by minus y square minus v. So, this is the expression for the velocity. So, and then as we have discussed earlier, so once we get the expression for velocity, we can find out the flow between the plate by integrating between 0 to b, and also we can find out the shear stress by taking a derivative of the velocity and then using Newton's second law. So, the velocity is known, and then also you can see that here now the distance y at which u is equal to 0 is obtained. So, here the case is that, say, I will just draw here the variation of with respect to the velocity, since the both plates, here this is moving with the velocity u in this direction and here it is v. Then you can see that if we plot the velocity, then the velocity variation will be something like this, since here it is positive. So, this is the velocity variation. So, the other direction like this. So, this gives the velocity variation for this particular case of the whenever two plates are moving in the opposite direction. So, you can find out here at this particular point, you can see that there is a place where velocity will be 0. So, you can just substitute the velocity expression which we got to 0, and then we can find out what will be this distance where this velocity will be becoming 0. So, you can substitute to the expression velocity is equal to 0, and then you will get that point. And then the discharge also, as I mentioned, you can just integrate between 0 to b, integral 0 to b u dy, and u is known, and then we can just get an expression like this. So, it is integral 0 to b u plus v into y by b minus 1 by 2 mu dp by dx into by minus b square minus v dy. So, this after integration we can get u minus v into b by 2 minus 1 by 12 mu dp by dx into bq. So, like this we can find out q, the discharge per unit width of the plate, and then also we can find out the shear stress distribution. We can just use the Newton's law of viscosity, tau is equal to mu into du by dy. So, u is known, you can just take a derivative of u with respect to y and then multiply by the dynamic coefficient of viscosity, we get an expression for the shear stress distribution. So, that is shown in this slide. Tau is equal to mu into du by dy, mu into u plus v by b minus 1 by 2 dp by dx into b minus 2y. So, this can be simplified as u plus v into mu by b. So, minus dp by dx into b by 2 minus y. So, similar to this shear stress will be 0 at a distance y, which is obtained by setting above equation to 0, very similar way what we have seen in the case of velocity. Shear stress also at between at some location it will be 0, we can equate the shear stress to 0 to find out where it will be 0. So, in all these three cases what we have discussed so far is, say, the laminar flow between two fixed parallel plates, and then a second case one plate is moving, and the third case both plates are moving the opposite direction. So, essentially say we are using the Newton's second law of motion, and then we consider the one fluid element, and then this is so called the first principle to derive the expression for velocity and other parameters from the first principle, and then finally we are getting an analytical expression for velocity and other parameters. So, now before closing this section, we will just discuss, say, as I mentioned earlier, there are a number of applications for these kinds of problems in fluid mechanics. So, we will just discuss one of the practical application as an example. Say what we will be discussing here is Q-tape flow. So, the Q-tape flow we have already seen that the lower plate is fixed and upper plate is moving, and then how it can be, say, the application comes. So, we will be discussing it here. So, the problem here is, say, now say as shown, say here a wide moving belt passes through a container of viscous liquid. The belt moves vertically upwards with a constant velocity V0 due to viscous forces. Belt picks up a liquid film of thickness T. Fluid viscosity is mu and density is rho. Gravity force tends to make fluid drain down the belt. Assume flow is laminar, steady and fully developed, and the atmosphere produces no shear at outer surface of film. Find an expression for velocity profile. So, this is a practical case, say wherever a bath of chemical or a tank of chemical is kept, in fluid form is kept, and then we just pass a belt through that, and then that belt will be carrying, since the belt is now the moving plate, and then the bottom of the plate, the tank is the fixed plate, and then with respect to the movement of the belt, it will be carrying some liquid, and then that is one of the application here. So, now we want to find out an expression for the velocity for this particular case, and then say once the velocity is known, as we have seen earlier, we can find out the shear stress distribution, or we can find out the how much is the carrying capacity, or how much the belt will carry. So, for this particular case is explained here in this figure. So, here the application of the Q-tape flow here. So, now our belt is, so this as the numerical example described there here. So, here now the belt is moving, this is the direction of the belt. So, here the belt is here the belt is moving with a velocity v0, and here this is the tank where the chemical in fluid form is kept, and then this is bath of fluid, and then you can see that since the belt is moving, it will carry some liquid with it, and then we want to find out an expression for the velocity. So, as described in the problem here, so some of the assumptions are assume flow is laminar, steady and fully developed. So, these are the assumption, and we are also assuming atmosphere produces no shear at outer surface of film. So, here this is the atmosphere which we consider here, and then the belt is moving up. So, we want to find out an expression for the velocity. So, as in the previous case, here also we consider a fluid element of dx by dy. So, this is x axis here, and this is the y axis. So, now to get an expression for the velocity, so we consider a fluid element of size dx dy. So, the control volume is considered here dx dy, and then as we can see here also the forces are compared to the earlier case, there is body force also. So, shear force is there, and then the body force. So, the forces are shear force and the body force. So, now with respect to this figure here, now if we use the Newton's second law, then we can write F Sy plus F By, that means the with respect to shear force and body force, that will be equal to 0. So, with respect to the previous figure, so if you consider this element, so F1 on both faces, F1 and F2 are the shear forces, and then Fby is the body force. Then we can write the expression as tau plus d tau by dx into dx by 2 into dy minus tau minus d tau by dx into dx by 2 into dy. So, this is with respect to the fluid element which we considered. Tau is the shear stress minus rho g dx dy is equal to 0. So, this is finally if you substitute the shear forces and body force with respect to the fluid element which we considered here, this is the fluid element which we considered. So, now with respect to while equating the body force and the shear force, we get finally an expression d tau by dx is equal to rho into g, where rho is the mass density, g is the acceleration due to gravity, and tau is the shear stress. So, this is the expression for this particular case which we consider here. So, d tau by dx is equal to rho into g, and now this we can integrate this d tau by dx, that once we integrate, tau is equal to rho g x plus c1, that is after integration, and that we can equate to tau is mu into dv by dx for this particular case, and Newton's law of viscosity. So, tau is equal to rho g x plus c1, that is equal to mu into dv by dx. So, that finally we can write dv by dx is equal to rho gx by mu plus c1 by mu. So, now finally we get an expression in terms of velocity. Our aim is to find out the velocity distribution. So, we get dv by dx is equal to rho gx by mu plus c1 by mu. So, this is the expression. Now, as in the previous cases, here again we can integrate, since now dv by dx we got an expression for dv by dx, that we can integrate to get an expression for the velocity. So, now again once again if we integrate, then we get v is equal to rho g x square by 2 mu plus c1 mu into x plus c2. So, this will be the expression for the velocity. C1 v is equal to rho g x square by 2 mu plus c1 by mu into x plus c2. So, again here we can have a boundary conditions, two boundary conditions to find out c1 and c2, the constant of integration c1 and c2 we can find out by using the boundary condition. So, here for the particular problem is concerned, we have seen that say here this is one of the boundary. So, here at whenever at x is equal to 0, that means on the face of the belt you can see that x equal to 0, then the velocity is already known, v is equal to v0. So, since the belt is moving with a velocity v0, at x equal to 0 we can write v is equal to v0, and then also since it is given as per the assumptions, we can get that at x equal to t, that means on this the say the fluid on the top of the fluid element which will be carrying, there it will be shear stress, we can write tau is equal to 0. So, that dV by dx is equal to 0. So, the first boundary condition is x equal to 0, v is equal to capital V 0. So, from which we can get C2 is equal to V 0, and the second boundary condition is at x equal to t, tau is equal to 0. So, that we can write dV by dx is equal to 0, from which we can get C1 is equal to minus rho g into t. So, where g is the acceleration due to gravity, rho is the mass density of the fluid. So, now C1 and C2 are obtained. So, finally, we can put back the C1 and C2 to the expression for the velocity. So, v is equal to rho g x square by 2 mu, C1 is minus rho g t. So, minus rho g t into x by mu plus C2 is v 0. So, v 0. So, this is the expression for the velocity, which can be simplified as v is equal to rho g is equal to gamma is equal to rho g. So, we can write v is equal to gamma x square by 2 mu minus gamma t into x by mu plus v 0. So, this is the expression for the velocity. So, the problem is again very similar to what we have seen in the earlier 3 cases. So, here one practical application we have discussed, we finally we get an expression for the velocity, and once we get an expression for the velocity, if we want to find out how much will be the carrying capacity or how much fluid will be carrying with respect to the movement of this belt. So, that say the belt is say the velocity is known. So, we can find out the flow rate per unit width, that is obtained as q is equal to integral 0 to t v dx as shown here. So, that is integral 0 to t gamma x square 2 mu minus gamma t x by mu plus v 0 dx. So, from which we can get q is equal to v 0 into t minus gamma t cube by 3 mu. So, this gives. So, now T is this thickness. So, with respect to this how much fluid it can be carried, we get q is equal to v 0 into t minus gamma t cube by 3 mu. So, like this we can get the expression for how much is the carrying capacity of the belt. So, like this various problems we can solve, say like now this is one of the application of the Q-tape flow. So, say there are various applications like this. So, whatever, since most of the problems what we considered so far, we are considering flow is steady, laminar, and then say the incompressible fluid is considered. So, with respect to these assumptions, now we are using the first principle, that means Newton's second law of motion, and then we are using the Newton's law of viscosity to supplement it, and then we are getting the expression for the velocity, shear stress, and other parameters. So, this is the way which we can solve the various kinds of problem. In all these cases, we are able to get exact solution, since the problem is say simple compared to other cases. So, we are able to get finally the expression exact solution for velocity and other parameters. So, this is about the first case which we, so first part of this laminar and turbulent flow, laminar flow between parallel plates. Or this you can see that here also lot of similarity can be, we can see that like practical cases like in an open channel, whenever a flow is will be considered in a flow in an open channel, then you can, if you consider both sides of the channel as fixed, then you can see how the flow is behaving, and then say with respect, as I mentioned, the application of Q-tape flow, whenever the one plate is moving, there are various applications in mechanical engineering, chemical engineering, etc., as we have seen. So, now the second part of this this chapter, laminar and turbulent flow, we discussing the laminar flow in pipes. So, here we are going to discuss the laminar flow in pipes. So, the pipe flow is considered. Now, we consider the here again the steady laminar flow through the circular tube. First, we will be discussing the flow laminar flow, and then we will be discussing turbulent flow in a pipe. So, first case is laminar flow in pipe. So, we consider steady laminar flow through circular tube, and here again we take the help of Newton's law of viscosity and second law of motion, as we have seen in the previous cases. So, now if you consider just like here you can see that if this is a circular tube and flow is entering from here and flow is leaving from the other side, for this kinds of simple pipes. So, our aim is always to derive say an expression for the velocity variation, velocity distribution of flow within the pipe, and then we can derive an expression for shear stress, and then also we can find out how much is the discharge passing through the pipe, as we have seen in the earlier cases. So, here if you consider a pipe as this is a simple tube. So, if you consider a simple tube like this, and then consider a horizontal tube of radius r0 and a concentric cylindrical fluid element of radius r and at length dx, forces acting on the free body of the fluid element we are considering. So, here this is the case we consider the flow is this is the pipe. So, the flow is coming from this direction and going like this, and the pipe is of radius r0 is the radius of the pipe. So, now as in the previous case again here we consider a fluid element. So, this is the first principle, as we have seen we consider control volume, small control volume, and then we see what happens to that control volume. So, here in the case of pipe flow also, laminar flow in a pipe also, we consider a small fluid element of size say dx length, and then from the central line of the pipe say we consider the radius to that the top of this is r, say we consider a small tube inside the pipe. So, at r. So, here now if you, for this fluid element is considered, what are the we will consider what are the forces acting, and then say once the forces are known, here it is steady state flow. So, we can equate this to the by using the Newton's second law of motion, we can equate the forces to 0 since acceleration is not considered, or in this case also. So, now if you consider here say at a if you consider the fluid element cylindrical, a concentric cylindrical fluid element of radius r and a length dx, and the radius of the pipe is r0. So, this is the case here. So, the forces you can see that for this fluid element is considered, here the normal pressure force will be P into pi r square, and the other side it will be at distance dx will be P plus dp by dx into pi r square, and then we have to consider the shear force. So, the shear force we can write with respect to this fluid element, we can write tau into shear stress multiplied by 2 pi r dx. So, these are the forces. So, in this particular case now you can see here the case we consider this pipe is considered as a horizontal pipe, but then if the pipe is considered in an inclined position, then it will be we have to consider the gravitational effect also. So, that will be considering later, but at present we are considering the fluid pipe is horizontal, and then we are deriving an expression for the velocity. So, that is our aim. So, here the forces are the pressure force P into pi r square on one side and P plus dp by dx into pi r square on other side, and then the shear force tau into 2 pi r dx acting on the surface of the fluid element opposing the motion with respect to the shear force. Now, as we have already assumed the flow is steady and tube is of uniform size, so that a total acceleration is equal to 0. So, that we can write du by dt is equal to del u by del t plus u into del u by del s is equal to 0. So, the total acceleration is equal to 0. So, that the Newton's second law of motion we can just equate the total forces to 0, since acceleration for the Newton's second law states force is equal to mass into acceleration. So, as per our assumption acceleration is equal to 0. So, we can equate total forces to 0. So, here say with respect to the fluid element, P into pi r square minus P plus dP by dx into dx pi r square minus tau into 2 pi r dx is equal to 0. So, the pressure force and shear force, and then we can simplify this as tau is equal to minus dP by dx into r by 2. So, this expression the force is equated to 0. So, that we can equate as tau is equal to minus dP by dx into r by 2. So, as we have seen in the previous case, again we can utilize the Newton's law of viscosity, tau is equal to. So, here now the flow is taking place in the right hand direction. So, we can write tau is equal to minus mu into du by dr. So, the shear stress we can equate tau is equal to minus mu into du by dr. So, once you substitute this expression tau is equal to mu into du by dr, we can get du by dr is equal to 1 by mu dP by dx into r by 2. So, this expression for tau is substituted back, du by dr is equal to 1 by mu dP by dx into r by 2. So, here again we get the velocity gradient du by dr with respect to r. So, as in the previous case, again we can integrate to get an expression for the velocity, and then we can there will be constant of integration can be obtained by utilizing the boundary conditions. So, here say now on integration we get u is equal to 1 by 4 mu dP by dx r square plus a. So, the boundary conditions here are at r, here one boundary condition is only one unknown. So, one boundary condition. So, at r is equal to r 0. So, that means when the flow takes place, you can see that here the fluid is going like this and passing like this. So, due to no slip boundary condition on the boundary of the tube or the boundary of the pipe, we can assume the velocity as 0. So, at r is equal to r 0 on the boundary of the tube or the pipe, we will get u is equal to 0. So, once we substitute back, we get the constant of integration here a is equal to 1 by 4 mu dP by dx into r 0 square. So, then finally, we can put it back this expression for a into here the expression for velocity. So, u is equal to 1 by 4 mu dP by dx into r square minus small r square. So, this is the expression for the velocity. So, now from this we can find out where the maximum velocity takes place, that we can get as if you differentiate and equate to 0 du by dr is equal to 0. So, you can see that where we can find out where the maximum velocity takes place. So, that is equal to 1 by 4 mu dP by dx into minus 2r is equal to 0 or giving r is equal to 0. So, you can see that at the center will be the maximum velocity. So, that is obvious for pipe flow, and then the expression for maximum velocity will be in the previous case, if you put small r is equal to 0, we get u max is equal to 1 by 4 mu dP by dx into r 0 square, and then a very similar way the discharge through the pipe we can get dq is equal to 2 pi r dr into u. So, here we can integrate between 0 to r 0, q is equal to 2 pi r into u into dr. So, that is 0 to r 0 pi into 1 by 2 mu minus dP by dx into r 0 square minus r square into r dr. So, from which we will get this is equal to 1 by 8 mu minus dP by dx into pi into r 0 to the power 4, and if we substitute minus dP by dx as minus delta P by L, the pressure drop, then we will get q is equal to the discharge is equal to pi into r 0 to the power 4 into delta P by 8 mu L, that is equal to in terms of diameter pi d to the power 4 delta P by 128 mu L. So, this equation is called a Hagen-Poiseuille equation. Here d is the diameter. So, the expression what we got the velocity or the discharge, this is called a Hagen-Poiseuille equation for pipe flow. And then as in the earlier case, we can get the shear stress tau 0 is equal to minus delta P by L into r 0 by 2. So, that we will get an expression for the velocity at the pipe wall, and then also we can find out the average velocity through pipe. Average velocity we can, so the total discharge is known, and then if you divide by the area of cross section, we get the average velocity. So, in this particular case we will get V is equal to delta P into r 0 square by 8 mu L, and from which also one of the parameters obtains like velocity, we can find out other parameters. So, the pressure drop also we can obtain from this expression for the average velocity as delta p is equal to 8 mu V L by r 0 square, that is equal to 32 mu V L by d square. And then from this we can get the energy loss per unit weight of fluid as delta p by gamma, which is gamma has a specific weight as 32 mu V L by rho g d square. So, like this various parameters we can derive, and then further we will be discussing for the laminar flow in pipes, and then further problems will be discussed in the next lecture.